Great. So yeah, thank you everyone for joining this talk and for your interest for REHO. So this acronym stands for a Renewable Energy Hub Optimizer, and it is a decision support tool for sustainable energy system planning. So my name is Dorsan. I'm currently finishing my PhD within the Industrial Process and Energy Systems Engineering Lab, EPFL, and it's a pleasure to introduce you this tool I developed with some colleagues from our laboratory. So very briefly, in a nutshell, the goal was to develop a decision support tool for sustainable energy system planning with a particular focus on energy communities and district level building stock and energy needs. So the key aspects, the perimeter for such a tool would be that it should be multi-criteria, so enabling multi-objective optimization. There is a strong importance on the considered territory. That's why we adopt a GIS-based approach. We also ensure the holistic approach by modeling the diverse end-use demands and multi-energies flowing through the districts. And a last very important point is the possibility to share equipment and for buildings to interact between themselves. So that's why we'll have some coordination between the different actors and their decisions. So the presentation will be quite brief. I will introduce the Renewable Energy Hub concept, then provide a few words about the mathematical formulation for the building and the district scale modeling. I'll say a few words about the availability of the tool and provide some references for all the documentation and all the code that is open source. And finally conclude with the applications and share with you some results and perspectives. So first, what do we want to model? I won't go in the very small details, but we use for REHO the concept of energy hub, which is simply a framework where multiple energy carriers can be converted and stored to interface supplies on one side and loads on the other side. So we'll apply this energy hub concept first at the building scale. So for the loads, we will have, for example, here the end-use demands for each building to satisfy. So for a residential building, we'll have, for example, the thermal comfort, so some heat or cooling load. We'll have some domestic electricity, domestic on water, and so on. And we have the supplies that come from the available grids. Then within, we have some building scale equipment to interface these two sides. And so these building scale equipment might be a heat pump, PV panels, battery, water tank, a natural gas boiler, and so on. And it's important to denote the availability of some local resources to be used. Now we can extend this same concept now to the district scale. So as loads, we have the previously mentioned end-use demands for each buildings, but we can also now include some mobility, some industries need, some ICT needs, and I can define the perimeter of my district and list the possible energy supplies. So as the supplies, I can have an electricity grid, natural gas, biogas grids, some carbon flows, some waste heat, some hydrogen, and so on. And I also have some local resources which are already available for this specific territory. Now for the energy conversion and energy storage technologies, to interface the supplies and the loads, we have some building scale equipment because each building can have its proper equipment, but we can also have some district scale equipment. So this latter being a shared infrastructure, for example, district heating network, combined heat and power, electric vehicles, seasonal storage, and so on. So now in the perspective of my district as an optimization problem to solve in order to minimize a particular objective, I can now distinguish the parameters from the decision variables. So what you see in green are the parameters, the end-use demands of my territory, the specifications of the supplies, for example, the cost, the carbon footprint, the availability of the supplies, the specifications of the unit, so the specific cost, efficiency, some life cycle parameter, and some local resources that are available. These are the parameters, and in orange, you see the decision variables. So now my optimization problem will be, will select, size, and operate some capacities to be installed. And this will define, so the equipment the optimizer decides to select, size, and operate through a typical year. This will define the imports and the exports of my district. So to summarize, the input of the tool is the territory end-use demands, which is characterized, in fact, by the building characteristics, the local weather, the unit specifications. And the outputs of the tool are the installed capacities, so some binary variables to select which equipment should be installed, what should be the optimal size, how should it operate through a typical year, and this will define the imports and exports of the district here, and also the building's interactions, because they will be able to share some energy. So now we have the inputs and the output of the tool. A few words about the mathematical formulation and what is inside. So each building scale, each building is defined as a mixed integer linear problem, where the constraints are the mass and the energy balance. Here you can see, for example, end-use demands have to be satisfied. We have some heat cascades and some building thermal model with internal gains and losses through the envelope of the building. And we have objective function that can be of economical or environmental nature, where multi-objective optimization is implemented through epsilon constraint. So every building will constitute a sub-problem. And now this is the important trick. We use a decomposition approach, because due to this network structure, having a single problem and trying to solve simultaneously the entire district will lead to exponential complexity, because the number of variables will grow exponentially. That is what you can see here on this picture. There is an computational complexity of the district scale problem if you try to solve all the buildings simultaneously, because they all connect to each other, because they can share equipment and energy. For this reason, we apply a decomposition algorithm, Danzig-Wolf, to keep a linear computational complexity. So the original problem will be split into many sub-problems, and one for each building, and one master problem. The sub-problem are the single building energy systems. They will send optimal design proposals to the master problem here. Like, we solve each of them independently. The design proposals are sent to the master problem, where the master problem is in fact from the district perspective, so from the exchange interface, for example, the electrical transformer or the connection for the district heating network. The master problem will receive the configuration and apply linking constraints, so the maximum capacity of the electrical lines, of the heating and cooling pipes and so on, to select the best configuration for each building from the district global perspective. So in the end, the district scale model is defined as again as a mixed integer linear problem, where the decision variables will now be the building's configuration selection and the selection, sizing, and operation of the district units. So here there is a picture which summarizes the master problem and the sub-problem interactions. As you can see here, some district level prices are sent by the master problem. So these are some district level prices, some internal prices only for the district. They are sent to every building. Every building will be re-optimized based on these dual values. So for the mathematical term, it's in fact the Lagrangian multipliers of their own objective function, and they will send new configuration, new optimal design proposals. The master problem will select the optimal ones from the grid interface and so on. And this iterative process will stop when the sub-problem objective values cannot be improved anymore by the Lagrangian multipliers of the master problem. So this is the core of the model. And then we can see here, as I mentioned, the inputs and use demand profiles of the district, the characterization, like the list of equipment that can be installed and the resources that can be used. And as output, we have some configuration, a design, operation, and this will constitute some energy flows within the district, so buildings interaction, and outside the district imports and exports. So yeah, a few words about the availability of REHO. Everything is written with 2 programming languages. So we use Ample for the core optimization model here. So for the objective, constraints, modeling equations, and so on, and Python for the data management structure. So initialization of the model, execution of the optimization, results retrieval, post-processing, and so on. And it's important to note that REHO works with both open source or license solvers. So it can be used for commercial or academia intentions. Here, some picture summarizing the REHO principal features. So as I mentioned, the MILP framework, multi-objective optimization, multi-scale capabilities, because we can conduct studies at the building or at the district scale, multi-service consideration, and multi-energy integration. REHO is deployed as a PyPI package, and the repository is publicly available. And we made an important effort for the documentation, including all the modeling details, some related work and publications, some guidelines, examples, and so on. And now I can share with you a few results, application and perspective, and how we use the tool to generate some results for some academic publications, but also for with industrial partners and collaborators. So, for example, we applied the tool on the existing building stock for an extensive study. So, for the case study of Switzerland, for example, we created a database characterizing the entire Swiss building stock. So it's more than 2 million buildings. And then we ran the tool over the complete territory, partitioned as 16,000 different district energy systems. So you can see them as energy communities. And it's interesting to compare some scenarios and to confront the economical, environmental performance regarding the different energy scenario that you would define at the national scale. Here is another example of a Pareto front, where you investigate the benefits of a storage, for example, and why it could be relevant to invest in some thermal or electrical energy storage. Here are some other diagrams where you can see the energy flows for a building, the annual flows resulting from an optimization for a renewable system. Yeah, here it's interesting. This diagram shows the evolution of the technologies based on the amount of money that people are willing to invest for shared equipment. So it's interesting to see that the self-sufficiency at the district scale can grow and be even greater when the decisions are coordinated. That is also something that is interesting here. The tool has been applied to study the trade-off between the grid reinforcement versus the PV curtailment. On this graph, you can see the yearly electricity profile for a residential district where PV has been installed, but when there is some curtailment that needs to be applied because the transformer has a limited export capacity. And it's interesting because playing with the peak power of the grid and the grid's usage penalty cost, we can see how the PV installed capacity or the PV curtailment will vary. This is interesting because at the moment, in Switzerland at least, the feed-in prices for electricity injection are very, they incentivize people to install a lot of PV capacity, but this PV capacity will not be it will not be compliant with the grid, the electrical grid capacity as it states for now. Talking about grid capacity, it's Also interesting to investigate the combined impact of heating and mobility electrification. So for example, when heat pumps, electric vehicles, and photovoltaics are massively deployed, because, for example, this plot shows the difference between the coordinated or uncoordinated decision. So what I mean by coordinate is every building takes its decision independently, or uncoordinated. And coordinated, it's when we adopt the transformer perspective and we have this master problem, sending some district level prices to make the different buildings so that they know the decision of their neighbors. So what we can see here is all the energy that cannot be exported when we take into account the transformer capacity. So we have the system that is curtailed, and we just see, of course, an increase of the OPEX. And we can see here the difference between when the decisions are coordinated, in contrast to when the decisions are uncoordinated. We have much more money that can be spent for equipment that will not have to be curtailed. A topic that can interest some of you: district heating and cooling networks are included in REHO, so considering various pipe size and temperature of operation. And for example, this is a work that we conducted with my colleague Daniel, that is also present here. This plot shows a total cost comparison for different configuration of DHN for a city of 13,000 inhabitants. So you have 5,000 buildings. Some diagrams showing global sensitivity analysis. This is a very interesting picture where we can see the optimal PV deployment induced by the various electricity tariff. So what we see here is that if the retail price of electricity is very high and the feed-in tariff is also high, all the PV investments are interesting. So it means that you would cover with such prices for electricity, retail, and feed-in, you would cover all your roof surface with photovoltaics, while here you wouldn't cover anything. And we have a continuous region between, where you only cover partially your roof, depending on the prices for the retail and feed-in of electricity. And this also can be a link to optimal configuration selection based on these variable energy tariffs. Regarding energy communities, we made some recent developments to include a multi-actor model, where we distinguish, for example, in the energy community, the owners, the one who will invest for the building scale equipment, from the utility, the one that will invest for the district scale equipment, and the renters, so the people that actually pay the bills for all the operational expenses. And it's interesting because we can compare the actors' profits and expenses according to the different energy system configurations. So yeah, there are some other information in the documentation link that I provide. Here I can also mention that there is also a graphical user interface that will be soon made available for also for people from the scientific or industry communities to play with the tool and to understand how it can be applied to various case studies. Yep, this is it. I provide you the link for the documentation where you can have some more insight regarding the tool. Thank you for your attention.